And Simon Fraser, and now she works on perception, human perception, and data visualization as a postdoctoral researcher at one of the top labs on that subject at Northwestern University.
Thanks. Thanks for having me here today. I'm going to share with you a couple of different research arms that I have in my research story. I'm going to ask us to challenge the idea of natural perception and what natural means, because I'm going to take us through 3 different digital displays where I do a lot of my research. And I'm hoping that together we can try to find some opportunities to take these results and use it to inform design principles and generally just best practices in user interface design. So the visual system we have, mostly living back here, takes up about 40% of our brains. It's phenomenal at what it does. Hundreds of thousands of years of evolution have given us tools like seeing these mountains here and knowing that they're not actually smaller than these trees are, they're just further away. We have that depth perception skill. We also have a little bit of prior knowledge to know that this down here is a reflection, because we know some properties of water and how light reflects off of water to give us a visual percept. Our visual system's really, really good at these natural environments and navigating. When we study them in the lab, usually these natural environments look a lot like this. So they're projected on a 2D space. We take this really complicated space, we put it on 2 dimensions, and we lose a lot of that richness that our natural system is meant to do. It's meant to do things like perceive depth and give us slight updates as we move laterally to see how far away something is or how big something actually is in the world. So many psychology labs are dedicated to understanding how we make sense of these natural scenes, and they usually do them in these 2D projections, or 2D projections poorly photoshopped on a laptop on a 2D projection of a vinyl screen. We do these things, we do these abstract projections in different manners. So one point I want to make today is that natural scenes are not just necessarily what appear in nature. The same visual system that makes sense of really beautiful natural environments is the same visual system that makes sense of 2D projections onto screens. Screens are a big part of our lives. I haven't yet found a survey that I trust 100%. A lot of surveys say anything from 9 to 14 hours of our day is spent looking at screens or interacting with screens in some way. Shout out to people watching this offline later. They're definitely on a screen right now. We spend a lot of time looking at screens and gathering information from them. So if we have a good understanding of how people are gathering information from screens and using it to inform their decisions, then we have a really good understanding of human behavior, at least in this day and time. So I'm going to take you through a quick tour of how I've been taking existing tasks and existing problems in the world, using that to better understand human cognition, and then how I'm taking those lessons from human cognition and trying to use them to inform design principles and design strategies. So very quickly, I'm going to go over some of my work where I look at how attention changes over learning, how that attention change develops as people understand a task better. We'll go into how that attention change looks really similar in a really different environment when you're not using your eyes, but instead moving your screen around to gather more visual information. And then I'll go into how I'm looking at the perception of data visualizations. And I'll just break perception. I'll show how it doesn't always do what we expect it to do. All 3 topics share a common property. They're taking existing real-world tasks and they're turning them into something that we can use to understand human cognition more effectively. Probably my favorite methodology remains eye tracking. I use it to track how observers sample the environment by moving their eyes around. They're complicated. Eyes are a complicated organ, and it only gets harder once you take the optical nerve back to the brain where it gets even more real. It gets weird, and we're going to talk about ways in which the visual system doesn't act like we would expect it to, even in a pretty simple environment. So I'm going to start simple. We're going to do a simple task together, which might be familiar to some of you. And we'll build our way up. I'm going to have audio here, if that's cool. Or not. There we go.
There's supposed to be sound here?
Yeah, it's okay. It works just visually too, though. Congratulations to everybody. Sure, is it too loud? That's perfect, yeah, thanks. Okay, has anybody not seen this illusion before who recognized the gorilla only on the replay? Thank you for your service. So in this task, you were asked to track the white t-shirts and the people passing the ball between the white t-shirts. So you're tuning your visual system to say, hey, I want to watch this ball move between white t-shirted objects. And it's tuning up your attention to white t-shirts, and it's inhibiting your attention to other features in the environment. So if you've seen this for the first time today, you might have noticed the gorilla walking past the display the first time around. And the reason why is because you set your visual system up for failure. You didn't mean to. I'm sure you did a great job counting those 15 passes, but your visual filters are turned up and down based on the task at hand. So one of the lines of research that I've done has looked at the impact of what our visual system expects to see and how it learns to expect the right things and inhibit the wrong things in the environment. When we go through the world, we take in a ton of visual information. If we ran this through a saliency algorithm, one of the old school ones, it'd probably say that this region here was the most interesting for the visual system. It would predict that most fixations would happen around here because it's high frequency and a little bit different from the rest of the environment. So the lesson being, salient images tend to draw our attention, but we can't just rely on algorithms to tell us where people will work all the time. The goal of the observer matters very much in what the eye movements look like. This is an old school saliency algorithm I was talking about. There's three major steps here. The first being the visual input, where it takes in color, intensity, and orientation. It runs through a couple of filters, flattens it out, creates a conspicuity map where it says this is the most salient part of the environment based on things like different intensities and orientations in the space. And it will say, this is the most salient region, this is where the eye fixation is most likely to take place. It'll predict that eye fixation to take place. Inhibition of return is a psychological process where it just keeps you from staring at one part of the environment over and over again. It'll tune that part down in your visual system and make other parts of the visual space more interesting to look at next. And that's how this iteratively does a relatively good job predicting fixations. But it's imperfect and we can break it. So here's a picture of Granville Street in Vancouver, where Simon Fraser University is. There's lots of nightclubs and stuff down Granville. It's a very interesting walk after midnight. And you can run it through the saliency algorithm, and it'll do a pretty good job of saying, well, these bright lighted areas are where people are most likely to fixate. We expect that high contrast regions, like the end of a neon sign against a dark sky, those will draw a lot of human fixations. So these algorithms can be really helpful for that kind of environment. What I'm doing, though, is I'm going to track people's eye movements, not while they're just free viewing a natural scene, but I'm going to give them a problem to solve and a task to learn. So I put them in this kind of display. I start out with a fixation cross to make sure their eyes are in the center of the screen. And then I show them this cartoon blood cell that we constructed for this task. So I separate 4 different features in space. And the idea being, you can look at 2 of these features together and get enough information to say this is an A category type, B category type, C, D. And you learn through trial and error. So here, these 2 features, I combine them together. I said A, oops, I'm wrong, it was actually D. So in the next trial, I'll query the environment differently. What I find in these sort of tasks is that eye movements do change as a function of learning. As people understand their environment better, their eye movements change. We know this. People have studied category learning for some time now. We know that pattern changes over time. So as people see more and more of these trials, their accuracy does improve. So it takes usually 40 trials to get a sense of a simple category structure. And we notice that they're looking at the features that are less important to the decision less and less as time goes on. So basically, as they get more accurate, they're being more efficient with their attention. So they're querying the environment in a way that makes sense to support the task at hand as soon as they get an understanding of that task. And they also get more efficient in that they just make fewer fixations. So this is the mean number of fixations per trial. As the task goes on, they make fewer and fewer. This replicates across different task environments. These are slightly harder category learning problems, but we see the same pattern of results. People learn it, they get more efficient, they ignore unimportant information. And we did a big survey of this. We did a 10-experiment paper where we looked at a bunch of different category structures and eye movements. Even within a single trial, if you set up the task that one feature is more important than the others, people's eyes will track that as they learn. So we normalize one trial over time. So that's one whole trial. And then we just look at the probability of them looking at the different features. Here, feature 1 is more important. It's more informative, so people will look there first. And as the trial goes on, then they'll look to other features as they become important. So people are indeed tracking, as they learn, the optimal way to solve this problem. So when I put salience versus relevance, knowing that as you learn how to do a task, and as you know how to do a task, your attentional patterns change, your eye movements change, and we are responsive to salience in the environment. So I wanted to see how those two things played together. Here you can see that one item changing in an array that looks the same will make it stand out and make it more salient. People have tracked eye movements to these sorts of problems before. This draws a very quick eye movement because it's the one salient item in the display, versus this one here, which draws a slower eye movement because it has to choose between two. So it's not just whether people look, but it's how fast they look as well. So we'll go through a trial. We have these 4 features. They can take on different values. They can be all of approximately equal salience, or I can manipulate it so 1 pops out from the rest of the environment more, or 2 pop out from the rest of the environment more. In all circumstances, these are not important for solving your problem. So a purely rational robot tackling this problem space would ignore those last 2 features and focus on the first 2. So a trial, show you fixation costs, show you stimulus with 0, 1, or 2 salient features, and then give you some feedback. Sure enough, people learn, pattern very similar to other category learning studies we did. People get faster over time, so that's one source of efficiency. And when we look at the eye movements using an eye tracker, so this isn't in their way, it just sits on the desk and records their eye movements, we find that people are more efficient in that they are not looking at unimportant information. But when they do, we find interesting differences. We find that salience isn't really that important. It's more the relevance that's mattering as to whether people are looking or not at different items in the environment. We find that relevance is really the main factor in drawing eye movements. So designers know this, right? When we're developing interfaces like this, there's a pretty clear call to action. People make it salient so people can find it pretty well. If this is your 4th time and you're fighting with yourself whether or not you need a new iPhone, and you've been to this page a number of times, you're probably immediately going to go to this buy button. It doesn't need to be necessarily all that salient. In fact, if you know it really well, we can make it super salient that there's another button there, and it's probably very easy for you to ignore that in the space. So when we're talking about developing displays for folks to interact with, we can think about the influence of salience in actually driving behavior, and it's a lesser influence than saliency algorithms might predict. If we're talking about eye movement velocity, we do know all things held constant, nothing else in the environment. Eye movements to a salient feature are quick. Eye movements away from a salient feature are pretty slow. So you have to inhibit that desire to go to a salient feature and then program and move your way to a less salient feature if that's the more important one for your task. When we look at saccade velocities in this sort of problem, with no salient distractors, saccades, remember that they're not terribly common to go to irrelevant features, but when they do happen, they tend to happen faster. So it's more reflexive. People are not really planning their eye movements in the same way. When there's 2 salient features, again, not often do people look at unimportant parts of the environment, but when they do, they tend to be slower. So it's almost as if people are looking at those unimportant items purposefully, and they're trying to see what information's there. And kind of the fun one is if there's a single salient irrelevant item, eye movements to are slow, as if it was important, and then eye movements to the non-salient distractor are fast. So we take this to suggest that maybe eye movement velocity is an interesting measure to indicate whether people are going to objects in the environment intentionally. It's a big statement. There's a lot to unpack there. And it's probably not 100% right, but it does seem from this data that after people figure out what their task is, when they're making fast eye movements, it's not 2 important parts of the space. So what does it mean for algorithms like this? the major lesson is we need another layer on here that says intention and desire of the observer for this to be a predictive algorithm in realistic environments. So in terms of theoretical applications, we can think about improving this by adding an intention layer. More recent algorithms do indeed make attempts for that. We'll talk about it a little bit in later work. Practically speaking, we can think about eye movement-based interfaces and how we could take data like the ones I've just described to say, if people mean to engage with parts of the visual display, will their eye movements look different? Will they be faster? Will they stay in the same space longer when they get to something that they mean to attend to? If it's errant fixation and they're just kind of looking at their environment, maybe it's less intentional. So we could take data like this and help to improve displays that are the basis of eye-based interfaces. Yeah, so eye tracking, again, it's a methodology I like very much. What I kind of was excited about for that project is we didn't need to use eye tracking to understand how people were solving that categorization problem. People were solving the problem anyways, and we supplemented it with the eye tracking methodology to further understand their behavior at multiple levels. And that's something I like to do. If people are doing a task anyways, how can we add a methodology and get more information from the environment? My whole thing being natural scenes and wanting to make it more inclusive, that argument is made. It helps me that video games are getting more and more photorealistic. So this I would call a natural interface. One's from a video game and one is not. When I found this image, I had to ask my friend from the Bay Area, please tell me which is not from a video game. It's this one. I guess the bridge is actually further away than they indicated. But this is another case where these are just basic flat digital displays, but they're photorealistic and they're approaching what we mean by natural scenes when we take them in the lab anyways. I'm not playing Watch Dogs 2, and when I started thinking about this kind of work, I was playing a lot of StarCraft 2. So conveniently, my game of choice is StarCraft 2 when we're talking about the day that are about to come. People generally in cognitive science, they're taking games a lot more seriously lately. We recently contributed to a special issue that was all about action video games for cognitive science. So it was just taking gameplay, in our case, gameplay logs, or taking gamers into the lab and watching them perform their task of expertise and see how it went. So we're not the only folks interested in games, but we are kind of unique in the way that we approach it. We have this background in category learning, and we are looking at eye movements. We realize when we're playing StarCraft 2, I'll show you some videos so you can see it, but essentially, you have control over a small part of the display, and you have to move your display so you can see more detailed information from the rest of the environment. So it's very much like making an eye movement around your visual environment to get more detailed results from the space around you, except it's with a mouse and you're moving your screen around with your hand. We actually use the same fixation algorithm that we use for our eye tracking data on our screen data. So the one-to-one is pretty strong as far as the back end of this. StarCraft 2 also has been having a really great week. It's on the cover of Nature this week. The DeepMind folks have created an AI who is better than all but 0.02% of StarCraft players at this game. It's a pretty exciting time for AI and video games in that they're doing great. It's a little bit humbling as a human who plays video games and doesn't stand a chance. But the algorithms that are out there are now able to beat essentially all of our best humans. Okay, I'm going to show you a quick overview of the game. Let's try with audio again. Hopefully this will work. It'll give you a general sense of what the game looks like and how it feels.
Greetings, Commander. Requested information follows. The strategic options in StarCraft 2 are endless, but the fundamental gameplay mechanics are simple. Gather resources, assemble your forces, and defeat your opponents. You will begin each match with a simple base and a limited number of workers. Use workers to gather resources. Resources are needed to expand your base and to train combat units. To overcome your adversaries, it will be necessary to assemble a formidable military force. Developing a strong economy will help you fuel the needs of your growing army. Each race, Terran, Protoss, and Zerg, has access to a...
So that's a quick overview of what the game looks like and feels like. Basically, it's chess if chess had too many Mountain Dews. It's dynamic and interesting. You're moving your screen around, and it's a lot like planning an army and organizing attacks. A few years ago, my colleagues published this paper. Then at the time, I was 25 and fought this title hard, failed. But I'm glad that I did because this got a lot of attention from a lot of folks. Turns out that StarCraft II does indeed bring people together, whereas we thought it might be a little bit isolating for a while. We got a lot of press coverage. Some of it remarkably missed what the paper had said. Here it's saying about how video games really do turn your brain into goop. Not the point that we were making in the paper. We were saying that older players tend to slow down. And your brain's already goop. So I'm not really sure what the point is that they were trying to make there. But we got attention from NBC, from the Vancouver Sun, from the AARP. And something that my friends back home are really proud of is we got attention from Perez Hilton, the celebrity gossip columnist. Super sad science deets I won't go into in terms of the back end of how we got this data into the system. But I will share with you some of the major measures that we use. We have papers coming out still that we're looking at by approaching these data in different ways. This is my colleague Joe, who was first author on the first StarCraft paper. He's describing a PAC, a perception action cycle. Come on, Joe. Okay, this video might not work out, but the goal of the video is just to describe what the perception action cycle is. So you have your console in front of you, you're looking at your game environment. You start in one, oh, it's moving? Oh. Oh, sorry, Press. There we go.
And this is for the Skillcraft project, trying to describe this new exciting variable perception action cycles. Essentially what these are these screen movements where you do something, and then you move your screen again. We're finding this to be a really important variable predicting StarCraft expertise. So you see I just moved my screen to my command center, and now I'm going to build a factory. The time it took to build that factory is this action latency. So what I'm going to do is show you another pack. First I'm going to select my command center, then I'm going to select my barracks, and the time it takes to do that will be my action latency. So it's important to note that we don't actually use screen movements in these analyses. What we do is actually aggregate some of the screen movements into these fixations using a Salvucci-Goldberg 2000 algorithm and throw out other fixations that are just noisy. And what this essentially does is remove some of the screen dragging that you see right there and focuses instead on when the screen is moved to a particular location for a particular time.
So this is kind of a fundamental unit of analysis for the StarCraft study. So we have our screen, we move it, we take an action, we move away, and that's a single perception action cycle. The reason why we choose this unit to kind of start is it's much like moving your eyes, and that's kind of our area of expertise coming in. It's a lot like moving your eyes. You move your eye to a new environment. How long does it take you to understand the gist of what's going on, and then interact with that new space? So Joe mentioned the action latency measure. That's one of the measures we have reported in a paper that is under review now. This is showing League, where League is, these are more novice players and expert players are over here. You'll notice significant sample size differences. It's a dog-eat-dog world out there. Not everybody makes it to the top. But generally, first action latencies are going down. These lines, I know they stand out a lot. This is kind of a quantization error. We can only sample the screen so many times a second. So those lines are broadly just, it's cutting off and sampling, cutting off and sampling. That's kind of what's going on there. So generally, better players are getting faster. And so that means something, either they're just faster humans overall, or they're better at anticipating what they're going to see when they move their screen to a new environment. We tried to isolate that latter part. They're better at anticipating what they see to a new environment by inventing this measure called new view cost. New view cost is the time it takes for you to interact with your space after you move your screen compared to all subsequent actions when you're there. So everybody's a little bit slower after they move their screen. This is the 0 point. Most people are above that 0 point. When they move their screen, it takes a little bit of extra time to plan that first action compared to later actions in the perception action cycle. But here again, we see that broadly speaking, better players are more responsive to the new environment than more novice players are. Going back to saliency stuff and planning out actions and priority maps, this saliency map is a lot like what we would use if we were talking about the category learning stuff where we have those salient distractors. So there's something in the environment, these little gophers, they're standing out as interesting. They're high contrast regions, they're different from the rest of the environment. More recent work in priority map space is making more effort in integrating what the intentions of the observers are and what the task is at hand. And a point that we're trying to make in this paper is that this architecture extends above and beyond just eye movements. It can also predict things like hand movements. So one of our points is that a lot of the architecture that helps us plan out where our eyes are going next and helps us understand when our eyes will be drawn to certain parts of the environment can also predict when our hands will go to certain parts of the environment, if that's how we're uncovering new visual space. It's also one of those hard lines that will fall apart at some point because you eventually need to plan the motor movement. But having an idea that there's a lot of shared architecture here will allow us to start to go in and falsify where this is not the case and diverge hand and eye movements away from each other again. So across the lab, using eye movements and in video games, we have a bit of insight into what the eyes and the hands might share in terms of brain architecture and planning movements. And also a general sense of the role of salience and the superseding role of task relevance and intention. The next chapter is another way of taking something that we already do in the world and taking it, simplifying it slightly, using it to understand how people are approaching that task by taking it into the lab. So we're going to look at data visualizations. A couple years ago, some folks did their own kind of saliency map. They wanted to start to predict human fixations. So they showed people this original display, and here's a heat map of the human fixations where people were actually looking. This is that old school saliency map that I talked about, where it just says high contrast regions. You might notice that it's pretty center biased. That's because newer versions of that saliency map have a center bias, which improves fits a lot. And then these folks came up with their own algorithm that would predict human eye movements in data visualization space. They look at the titles. That's really what people are doing with their eyes when they're looking at data visualizations, which I take to mean that people are going into a task like this, and they're trying to get a sense of what the task relevance is, what the context is, and what their goals are from the rest of the visualization, which is telling me again that it's more the higher level, top-down stuff that should be driving how people are accessing information. There are a few of us who are interested in this intersection of data visualization and vision science. We are led by a group of up-and-coming researchers who organize these InfoVis by Vision Science panels. They've let me be part of workshops at the Vision Science Society and at the IEEE Viz conference. So this is where vision scientists tend to go, and this is where a lot of people from the data visualization community tend to go. And by hosting workshops at these different spaces, they're trying to get people in these two worlds to talk to each other. I was able to organize an event last year at the Cognitive Science Society with a couple of colleagues where we brought together a bunch of folks who are interested in data visualization but at different levels. So we had, for example, Karen, who does relatively low-level color perception stuff in visualization space. And then we had some folks who are more at the level of decision-making, higher-level cognition, philosophical, like how do we approach meaning in these sorts of spaces. And we just tried to connect a common thread between all these different ways of analyzing how humans behave when using data visualization as a test case. So one of the reasons I'm excited about being in data visualization or in video games is to take ways that people are doing tasks already out there in the world, and we can use them to unify multiple ways of thinking about those tasks from communities that might otherwise be siloed, often against our best efforts. To go through a couple of my own studies quickly, this first one's a simple ratio perception study. So what's this bar represent? Good job, it's 48%, or it could be 52 billion. We don't know, it has no context. And that's kind of the point we want to look at. This bar, without some sort of context around it, only means something if we go in with a set of assumptions or we have an idea of what we want to see when this graph shows up. Okay, all right, now I get to see this 48, 50%. And we can also do the stacked bar graph where it's pretty clear, okay, this is actually a subset of this whole entire space. And it's a really simple bar graph. It's not doing much above and beyond, just saying, I am this high, I mean this much. So what we did is we got people in the lab, showed them a bar like this, took it away, and then we asked them to redraw it in a different part of the space. And we looked at how far off when they were when they redrew it. And our idea was, people should be pretty accurate about this. It's just a bar. So we tracked people's errors. Across the 3 different conditions, we had the bar by itself, a bar graph, or a stacked bar graph. And we showed them everything from 1% to 3, all the way up through to 99% out of 100. And we just tracked to see how far off are they when they recreate this bar in a different part of the space. So we'll leave this here as kind of a sample. This is a 50%, but we did sample everything from 1 to 99. And we'll look at the response error. So when I say response error, I just mean, were you off by 1%, or were you off by 5%, or were you off by 50%? That's how many percent points are you off? Is there a question?
Height is the only metric for the
Height is the only metric. We hold width constant for now. We're just looking at really the height of the bar. This is a lowest fit of how people performed with the bar only condition. So generally they overestimate for a little bit, but as soon as we hit about 25%, they're underestimating the size of the bar. So for all of these, the left of the axis will be underestimation, and the right will be overestimation. And we find that bar graphs, again, largely speaking, underestimated. And then we have the perceptual system just having a party here where it breaks entirely in the stacked bar graph condition. As we approach this 50% mark, people are underestimating the value that's being presented. And as soon as we get past that 50% mark, people are overestimating the value that's being presented. So in all 3 circumstances, we tend to see overestimation for small values. And this repulsion around 50%, that is a little bit dangerous. If we could trust one thing in this world, we thought it was bar graphs. And they are doing us a bit dirty here. So there's a couple of things that we did that we were able to pick up on this bias. By sampling the whole range, we were able to get a sense of what the response patterns look like across the whole ratio space. And by showing over and underestimation and not just error, we were able to tell bias patterns as well. So a lesson from this, there might be certain types of bars that are more appropriate to encode data based on the problem at hand. If there are 2 political opponents who are differing by 49 and 51%, this is not the way to do it. It's going to feel like those 2 opponents are more different than they actually are. In some ways, you'd almost prefer that they're 2 separate bar graphs by themselves so that the difference is not amplified. It just is maybe, if anything, both will be equally underestimated. OK. We had a few things going for us. One, my background's in category learning, so I know a little bit about categorical perception. So I wasn't totally shocked to see this happen. We do have a sense, when we show a full range of values, that we do anchor to the ends. So usually when you're designing data visualizations, if you can use flat ends of your graph to encode the most important data, that's a pretty good practice to follow. And another thing we had going for us with that study is we had a general, almost an intuition that people were using ratio-based processes to make these judgments when they were reading bar graphs. As we started writing it up, we realized that the best way we had to describe it is we had almost an intuition that people were using these ratio-based processes. And we realized, OK, there must be other things that people are using in data visualizations that we're not challenging because we're not aware that they're processes that are being employed. So in this study, we showed people a bunch of different kinds of graphs, and we're just trying to get at what perceptual processes are you using when you read these things. So we tested out 5 different visualization types, and we had them perform 10 different tasks. This is an existing taxonomy that's been around for a while, so we borrowed that taxonomy and said, please look at all these different kinds of graphs, and we'll give you prompts that encourage you to do these different types of tasks. And what we did is we interviewed participants while they did this. So let's play together. I'm going to show you a graph in a moment, and I'm going to give you the task, sort the top 3 values. Have a look at that. Inquire to yourself, what visual processes am I using to sort the top 3 values here? A lot of people will report, they're saying, OK, well, I have 3 that are high enough to be contenders, and then I'm going to take those contending high bars and organize them after the fact. Same game, different graph, sort the top 3 values. Oh, all right, now I need to maybe look at one slice at a time, compare it to its neighbors, figure out what the biggest ones are. It might feel like your eyes are doing a bit more of a dance where they're going around the space, sampling the slices, and trying to find out which are the biggest slices here, and then I will sort them after the fact. So it's a single task, 2 different graphs, and we're noticing different visual processes are probably at play here. One of the major lessons we had in looking at the data after we conducted the interviews is that different graphs do invite different perceptual tools, even if the task is held constant. My perceptual tools, I'll talk through what we mean. You can have a graph like this and one item will pop out based on its size compared to the rest. We just call this pop out. There's a large literature in perceptual psychology about this phenomenon. Pop out probably encompasses 2 or 3 slightly different things, but is a way to categorize processes that we were observing in our data. Same graph might be subjected to a distribution process. So you have a sense of the size of the circles. They're mostly normally distributed. You have very few small ones. You have one big one that's throwing the distribution off. But generally, you're computing a distribution of the size of the values. You could judge shape. You could create an envelope around all the dots and say, well, generally, it's a downward sloping oval. Or you could filter based on one of the group properties. So you could say, well, I want to try to determine a correlation with just the pink group. And you can turn up that pink filter and turn down that orange filter. And you could risk missing a gorilla, but you'll have a subset of your data that you care more about that you can operate on. So with these 4 perceptual tasks, we go through our interview process. We show people all these different visualization types, ask them to perform these tasks. That's a photo of me interviewing people. All right, and I'm just going to let you listen in on one of our interviews here so you can hear the kinds of things that people are saying.
Month and temperature. I mean, I guess I would say yes, considering like the shades aren't random. Like they very much transition slowly from in an order that makes a lot of sense, from the darkest color to the lightest color, from January to July.
Can you give me some insight into how you know that they're not random?
Yeah, because I would say the tone, like, or the color makes small steps towards the next color each time. And like it flows very smoothly, whereas like if this color was like there,
yeah,
it wouldn't look like a smooth transition, whereas shade-wise, they just seem to make equal, sensible steps towards the brightest shade. So I would think there is a correlation of that, like it gradually, just like the colors gradually get warmer and warmer and warmer, the average temperature of the month gets warmer and warmer and warmer.
Right.
So that's the kind of thing we did. We just had people talk us through what their eyes and what their visual system was doing when they saw those different graphs. And then we took the videos that resulted from the interviews, we coded them after the fact to look for these 4 different perceptual processes. In this circumstance, that participant was performing a correlation task. Going to show you the same task using a different visualization type here.
There's definitely a positive correlation between grade and class size. Generally, as grade increases, so does class size. There is the exception of the jump from 11th to 12th grade. It looks like 10th and 11th grade are all bigger than the 12th grade. I'm slightly confused by the axis, but otherwise I think it's pretty clear that there is a positive relationship between grade and class size.
And when you start to answer this question, are you filling any magic shapes and lines and boxes or anything in?
Yeah, obviously there's the exception, but when I said there's a positive relationship, I imagined myself drawing a line from grade 1 to the maximum corner of the other side, so there's a positive trend.
Okay. You probably have a sense, I know you've seen 2 of these trials, but you have a sense that when I'm looking at a heat map versus a bar graph with a participant, people approach it differently. That top-down, the goal strategy is going to really impact how they're approaching that. But also the basic visual perceptual tools that they're using differ based on what kind of visualization I'm showing them. So one of the other lessons we have from this data is that when we show people different graphs, they use a different set of these perceptual tools, even if we hold the task constant. Similarly, probably not going to show videos on this right now, but if we give people different tasks using the same visualization type, then again, we see different people use different perceptual tools. And finally, we take all this to suggest that using these 4 perceptual tools, we can get a more basic understanding of how people are approaching data visualizations, and then we can take them into the lab and do like we did with that ratio study and break it and see where it breaks and suggest design innovations around avoiding failures of the perceptual system. So those are the 3 major points from this qualitative study. This was my first foray into qualitative data, and I will admit I was pleasantly surprised how informative it was. Participants were way more insightful than I expected them to be when I interviewed them about how they were approaching problems, what processes they thought they were using, and they were super responsive as I tried to get them to dive deeper while trying to avoid leading them as best I could. One thing we can do is we can take the results of these sorts of data and take them into recommender systems. The best paper at the visualization conference either last year or 2 years ago was a recommender system that took in what we kind of know about human perception and used it to inform designers as they were trying to create their own data visualizations anew. If we understand where the perceptual system starts to falter, we can put that into designer systems and help people avoid designing systems that are not going to help support our perceptual system do its job the best. Okay, so these 3 things, they're taking a real-world task, and they're trying to help researchers better understand how people are interacting with that task and how the human cognition works more generally. We have eye movement stuff that suggests that the velocity of eye movements can suggest whether or not people are accessing information in an intentional way. We have the video game stuff, which suggests, shockingly, better players are faster, but also suggests that there might be correspondence between how people are interacting with a manual digital display and how people are interacting with an ocular motor sampling of the visual environment in the real world. And we have our perceptual system, which is amazing, but is kind of trash at the one job we're trying to ask it to do here, or at least under certain environments, it does fail us. So knowing when it fails us and how systematic that is will help us to design around known issues in the perceptual system and help to design innovations around those sorts of shortcomings of our pretty impressive but still fallible human brains. Okay, so at this point, I think I'm going to invite some questions, and for anybody who's watching this after the fact, you're welcome to email me. I'll share my email address and stuff so you can get in contact. But here, does anybody have questions or clarifications for anything we've talked about today? Yeah. Oh, thanks. Yes.
Hi. So I'm really interested in novices versus experts behavior. And I don't know if, particularly if there's interesting interactions with it. For example, just to take the last one that when you talked about the different, was it visual tools, I think you called it, for perceiving things. Would you see a difference, could you potentially see a difference between novice and experts? Is there some graphs that are going to work better for some novices than compared to experts? And then I'm also interested in the whole process of what it takes for novices to get to experts. So
Sure.
There's a lot of questions there. So
Yeah.
you can pick and choose, and
Okay.
or what do you see as the interesting questions there, and if you know answers?
Sure. I don't know if I know many answers. I'm interested in expert-novice differences too. One of the things about the StarCraft study is it wasn't just experts and novices. It allowed us to kind of sample how that develops over time. We had intermediate players too. So it's something I think about a lot. With the visualizations, we were a little strategic in using bar graphs for a couple of reasons. One, they're super simple, so there's not a lot of confounds to isolate out when we want to make causal statements in the lab. But two, most people who come to Northwestern University have enough experience with bar graphs that we would think that they would be experts. That's probably a very dangerous assumption. So that's something that I think you would almost need to look at developmentally to have a whole picture of. Because we can't control how much exposure people have to simple visualizations before they come in the lab. Because I have a bit of background in categorical perception, I would anticipate even experts would be subject to that kind of bias, because it is really like, visual system has a lot of layers kind of going back up. Back here, that second layer is the one causing this bias. And I don't think you can expert your way out of that problem. You might be able to correct after the fact. And I think that would be an interesting group to run on. People who, maybe folks like data science students who spend a lot of time looking at graphs and are really well informed as to what those numbers actually are and not just what the visual is. Those would be interesting populations to look more into. I haven't looked at it yet. Yeah, but I suspect if I rushed people through it, I said, draw these graphs as fast as you can, they're going to be almost as bad as novices. But I think experts, if you give them time to make a response, are probably able to lean back on their wisdom and correct what their initial response is perceptually, if that makes sense. It's an open study to run, though.
Trying to also sort out the difference between expert and novice, where this amount of practice and training that they've had versus, I don't know, some natural ability or whatever as well. And I guess you also have that with the game problem as well, right? Are they better at those levels because some ability, or is it because of all the practice that they've done?
Well, that earlier paper suggests that if you're 24 and under, that's to your benefit. To be fast in making those game movement operations, right?
But
that's a factor.
Okay. Did they really sort that out though, in terms of the practicing, or I don't know?
We have as covariates in those early models the number of hours people played,
Okay.
self-reported.
Right.
But I don't have a lot of reason to say that people are going to lie about all of it all the time across thousands of participants. I should say, even in our novice sample with that video game study, our novices played for 300 hours. Like, our novices were great. Our grandmasters were just truly phenomenal. So expert novices has a lot of cultural connotation too. I think our novice population is most people's expert population in the video game study. And then even in my category learning stuff, maybe a novice is people starting out in that first block of learning, and then by the end of it, we can call them experts. So I think it's very domain specific what you mean by that distinction.
I have a follow-up question to that. I mean, have you tried maybe incentivizing the responses, maybe $100 Amazon gift card, something like that? Would that make a difference?
Are you funding it?
Something like that?
Yeah. In my dissertation work, I had people looking, this is going to be kind of a long story, but there's a special kind of graph that people use in business called a candlestick chart, which was new to me. Apparently a lot of people knew about this, but it's a little bit awkward to read. You have to look at a box and then kind of flip it if it looks a certain way. It's worth looking up. They're odd little displays. And I had people make gambles, and it wasn't really incentivized in the sense that they didn't walk away with much, but I had them actually try to accumulate as many points as they could in this universe that I created using these candlestick plots. So it's kind of a complicated graph to read. Generally, you could see overarching trends and then little nuances within. And when people were working towards points, they were incentivized. Like, gamifying the problem space just made people want to try harder. In terms of the data visualization stuff, I'm not sure I would be able to, I'm not sure I would be able to incentivize people to be less biased here. And that goes back to our earlier question. I don't know how much of this is something we can overcome when we have this categorical repulsion going on. I'm sure people are going to try harder if they walk away with $100 and they do well. But I'm not sure above and beyond removing context if that would be more effective. Because here, without the context, folks are underestimating pretty consistently, but at least they're not treating 49 and 51 as way different than they actually are. So it's kind of a choose your battles situation. Sure, Eli?
So I noticed when you have this one up here, yes, there's a lot of kind of, on the stacked bar there, it's clear what area you're pointing at, but there's also basically no uncertainty around the measurement at 50%, which is very striking to me, right? It's like over and underestimation are a serious problem, but when it's at 50%, no one's confused about it.
So that's coming from the way that I fit this data. I might have the raw, I might have to show you the raw data after. But what happens is if you look at each data point and you show them along this plot, it's almost feels like it's going like this, but there's more data coming here, more data coming here, and then that 50% is almost totally unbiased. So it's poor in terms of accuracy, but phenomenal in terms of being unbiased. So if you and I both look at this, and we want to, you're looking at something that's 49, I'm looking at something that's 51. I think I'm likely to overestimate it. If we're both looking at 50, I might be just as likely to underestimate it, and you might be just as likely to overestimate it by the same degree. Yeah, so it's kind of a fascinating set of data for such a simple task. It gets pretty complicated. Yeah.
I was thinking about the StarCraft study, and it reminded me of some of the things that I've talked with students about in terms of multitasking. And so I wonder if you, in that, try to tease apart, well, what is the perceptual, the time perceptually that it takes, you know, if they're moving to a different place to take in everything, and cognitively, I guess, in terms of what's assessing the situation. Maybe it's just too difficult to tease those two apart because there's the perception aspect and the cognitive aspect are just too deeply intertwined.
Well, and to just pile on top of that, we know that the frontal lobe shrinks, and 25 is considered the time when it starts to shrink. So I'm wondering how much of this has to do with just working memory and less to do with perception.
So if you dive pretty deep into that aging paper data, the folks who are still doing well, so we have that league 1 through 7, the folks who are on the higher end of that league space, but exceeding 25, we have people who are 40-ish, and they're still competing really well against 20-year-old players, but they're smarter in the way they play. So I don't think I'm going to say that any deficits we're seeing in speed are a function of frontal lobe decay. These are bold statements for this data. But yeah, if I were asked to speculate, I would say that it's not that people are planning any less well, it's just that the motor execution's slowing down. Whether I can say it's perceptual or cognitive, unfortunately it's probably both, right? If it was, I can take this problem space into the lab, strip out a lot of the nuances, and I could say with more confidence whether it's perceptual or cognitive, and we've already done that. That literature exists out there, and it's a matter of trying to now take that simple lab study and this complicated game and trying to bridge them a little bit. In the game, there's so much about being surprised and expecting what's happening. The metagame, people study videos for hours and hours and hours to know what's likely to happen as they leave their base. And at time 5:02, I'm expecting this unit to come and attack from this angle. So expert players are less likely to be surprised. They have less to take in. They're looking for violations of expectations that are constantly reinforced. Novice players are more likely to be surprised. I think that surprise component, it's very much about expectations. And what are your expectations? What's your priority map going into this new environment? And if your priority map is violated, then you update very quickly, but that's some cost to your motor execution. So I need to update what my plan was. That means now I need to cancel what I was about to do with my hand, reinitiate a new movement, and do the second movement with this new plan because I was surprised by what's in the environment. So sorry, you started this with multitasking.
Well, it's about, how much of it is the cognition and how much of it is the perception. And I was also just thinking about, you described this as being like chess on too much Mountain Dew. And then it occurred to me, well, you know, you don't see, as far as I know, Grandmasters chess players who are all under 25 years old. So there's a bigger impact of expertise there, maybe, as opposed to how quickly do you move, but there's less pressure to be fast moving.
Yeah. Do Grandmaster chess players retire? Or do they? Yeah. I'm curious if it goes like this or if it's just like this. I don't.
Good question.
Yeah. That's something I should know and be interested to look more. Right. Fair.
Maybe get old.
Yeah.
It goes like
It does decline at some point. Okay. Yeah, so perhaps it's just you're relying more on the planning and knowing what's coming and less on the reacting to surprises in the environment. Because we know if, I think it's been around for a while now, people take expert chess players, put them in the lab, and give them nonsense boards, and they're no better at novices, at recognizing.
So that perception aspect is there.
Well, that could be cognition too, because it's an expectation.
Whether they can recognize, they can just look at a board that, you know, they're not expecting to see a board, but you show them a board that makes that would occur in a game, and they can categorize that as to what's going on there quickly and remember it.
Mm. Yeah.
But is that all perception or is that cognitive as well?
Well, people get in super heated debates about whether sensation ends, perception begins, and then cognition happens.
Right.
I don't want to have that fight. I don't know how to have that fight productively, but I think in that case, if you show somebody who's really, really comfortable with a chessboard and what it might look like and what's a reasonable chessboard to see, it makes sense that it's easier for them to go on to an existing scaffold, an existing almost semantic representation of what that thing in their space is, to then encode it differently than someone like me who's like, I'm pretty sure that's a knight, and it's here. So we're approaching that problem differently, and the way that we're storing that information, for me, it would probably be perceptual, and for an expert, I suspect it would be much more semantic, or at least at a different, deeper level of cognitive processing.
Quick question.
Sure.
You mentioned this recommender system, this work on recommender system to recommend visualizations. Can you elaborate on that? I know that's not your work, but...
Sure. Yeah, so the name of the recommender system I have in mind right now is Draco. The lead author on that is Dominic Moritz. What they do is they take a sort of grammar of visualization. That's the sort of language that they use. So if I have an intention as a designer of doing something like, I want to see the correlation between variable A and B, and I give it to a system that can see, I scanned over this data, these are two numerical values, this is a viable comparison to make, then it would probably lead me along through my grammar if I want to correlate these two variables that are actually correlatable variables. It would lead me to the process of eventually just making a simple scatter plot. So the recommender system is a way to guide a designer through making the appropriate design decisions for what their intentions are without stomping out any creativity. So it's like, here's what you probably want to do, but it's not saying this is the only way to represent these two different types of information, or these two variables in your information display. Recommender systems are really broad. Draco's the one I probably know best, but there's other ones out there that would approach that problem in different ways.
Any more questions? All right, then let's thank the speaker once again.
Thanks for having me. Thanks for coming out on a Friday afternoon, too.